My name's Val Henson. I have my own company, VH Consulting. I specialize in Linux file systems, but I do all sorts of other systems programming stuff too, especially silent data corruption. I love trying to find out what's going on with silent data corruption. Anyway, so I have this research agenda I've been going along on for a few years now, which I'm summarizing as repair-driven file system design. The idea that it's really important to design your file system so that you can repair them quickly, as well as access them, write things to them, delete things from them, all your sort of normal online use. So the way I got started on this initially, oh, by the way, this is the Chunkfs talk. It just starts out this way because I think it's bigger than Chunkfs. So this is a question that got me started. And when I initially asked this question back in 2002, I just started working on file systems. And the way I answered it was, in my head, was, well, disk capacity will continue to grow. But CPUs will get faster, too. And then there will be no problem, right? Because at that time, I thought file system check was CPU bound, which it is not. Not even close. So when I came back to this in 2006, something like that, I actually did some math, which is very dangerous. Math can find out all kinds of interesting things. So first I started out with these, some numbers I grabbed from a Seagate paper, which is, the vendors are the best reference you can get right now. So their predictions for the way that disks are going to change between 2006 and 2013 are thus. Capacity will go up by 16 times, which is sort of the normal expected doubling rate we've seen for a long time. Bandwidth's only going to go up by 5 times. So bandwidth relative to capacity is going to be about 1/3. So that's uncool. And the really crazy thing is that seek time is not going to change. It's like some incredibly minor speed up that they're expecting. I had a really cool personal experience with this recently. One of my friends bought an ancient Amiga UNIX machine. There was such a thing. It ran UNIX. Off of eBay. I think it was built in '92, something like that. And there's a program you can run to find out the performance characteristics of your drive. And it could do about 40, 50, 60 seeks per second. There were 2 different drives. One was doing 40, one was doing about 60. This laptop can do 70 seeks per second. So what is that, like 15 years? We've got another 10 seeks per second. So ouch. OK, so using my laptop again, because that's what you do, I decided to do some math to figure out how much file system check time would change between 2006 and 2013, assuming my file system grows as fast as the disk. So you can see the numbers here. I tried to be I gave CPU 0 seconds, assuming my CPU is infinitely fast. I came up with this really bad prediction, is that my laptop in 2013 will take 80 minutes to run a file system check, which makes me really upset. I really don't like that it takes me 8 minutes right now to check my file system. This is clearly not the way to be going. The way that file systems are designed right now and the way that all future file system development is going is such that this is going to be the result. All right, so I'm going to get through this pretty quickly because lately people have been buying this. You can say, OK, great, file system check is going to take a long time, but I'm going to have to do it very seldom because disks are so reliable and stuff. So there's a bunch of things that are going to cause you to have to run file system check. The per bit I/O rate is going down. The per disk I/O rate, error rate is not looking so great. You can do all kinds of bad stuff to your disk on purpose. Failure of layers below block device interface. I think SSD, compact flash, all that kind of solid state storage stuff, really, really, really bad error rates. So that's even more of an issue than before. And then there's always file system bugs. If you can eliminate every other source of error, you're still going to have bugs in your file system. And those are going to be the hardest to fix and find. There's also even more edge corner case where your operating system has bugs and ends up like stomping on the thing that you're writing to disk. It's not good. OK, so yeah?
Which of these broad categories would unexpected power cycles fall into?
So unexpected power cycles is something that the software is designed to handle. So modern file systems all can handle that to one degree or another. Does that answer your question? Or?
Okay.
Yeah. So this is a lot of people. I think I have this in the next slide. We'll see. Okay. I think I have a further comment on this. So I'm calling this the FSCK time crunch. I want to emphasize right here that FSCK is actually including file system check and repair. It's wonderful if you can check your file system really quickly, but if you still take a long time to repair it, we're still losing. Presumably, we're running file system check because there is something wrong with the file system. Okay. Yes, this is the point I wanted to make. So a lot of people, when I bring this to them, they say, well, that's what logging is for. Logging is actually just for handling the case of an unexpected power cycle. So in the good old days of FFS and ext2, you just write stuff to the file system in any old order, and when if the machine crashed unexpectedly or there was a power cycle, then the on-disk state was kind of undefined, and you had to go and fix it. Modern file systems use logging or copy on write or something like that, so that they can recover from this very quickly and deterministically and get it right. So that's not what I'm talking about here. What I'm talking about is actual errors of some sort. So this is the next objection I get a lot. Is, oh, we don't need to do that. RAID does that. Well, RAID, honestly, I think it's questionable whether it improves stability. I've heard of so many RAID disasters. It's like RAID isn't tested very well. Usually it works, and it's when it doesn't work anymore that things go wrong. There's a huge problem with latent sector errors. If you lose a drive and you try to reconstruct it, you suddenly discover that 5 sectors on your other disks are bad. So it doesn't fix it, trust me. And so there's still the file system bug case. So I proposed repair-driven file system design. This is the idea from the very beginning, assuming that you're going to have your file system is going to break, and you are going to want to fix it quickly. So a bunch of stuff that I think should go into it. Start out from the beginning, thinking about it. This is a hard one for file system programmers or programmers in general. Simple data structures. We like to be really super clever. It is way more fun to come up with something complicated. When you start thinking about things in terms of, OK, this has been broken, how do I fix it? Suddenly you want very, very much simpler data structures. The metric I like to use is, could you repair this by hand? If you can't repair it by hand, you probably can't repair it automatically in your file system repair program. So we currently lay out data on disk to optimize for reading or writing or directory traversal or something like that. There's not much thought given to optimizing it for the order in which you need to traverse the data in order to do file system check. So most file systems lay things out right now so that if you're walking the entire metadata tree for the file system, you end up doing all of these seeks and dependent reads and things like that, which, as we know, we can only do 70, 80 seeks a second. So that really cuts down on the speed. So I forgot to edit this slide because this is very important. Fast incremental file system check and repair. So the incremental part is very important. I just don't see any way to make file system check go fast unless you can do it one piece at a time. If you look at the bandwidth of the disks, it's going to go up by 5 times. Capacity is going to go up by 16 times. I mean, if you have to read the same amount of data, you have a very strong limit on how quickly you can go. So the repair part, again, you need to be able to repair it quickly and incrementally. So, OK, all this stuff people know: checksums, redundancy scrubbing. You should just have 2 copies of your metadata. Metadata is so little overhead on most normal file systems that you just might as well keep 2 copies of it. This still isn't going to help you in the case of a file system bug, because if you have 2 copies of the wrong thing, it's still the wrong thing. So, and this last principle, I think, is probably the most generic and one I would like to see adopted widely is metadata isolation. So if I screw up this one piece of metadata, how far can the repercussions of this travel? Can this ruin the free space map for the entire file system? Okay, that's bad. I'm going to try to limit that. Okay, so this is my particular iteration or instance of these principles. It's presented as Chunkfs, a file system. It's actually more like a set of techniques or a meta file system. I am debating whether it should be implemented on its own or just folded into new file systems. So the idea is, great, ooh, exciting, divide your file system into sort of little file systems. And I'm calling them chunks. Because that's what you call, there's like 3 words that you get to use in storage. It's like blocks, chunks, and I don't know, sectors or something like that. And people just use them over and over again. So I'm using chunk. So you divide these up into independent little file systems. Great, I can check each one of them individually. The problem is when you want to share the space and the namespace between them all. So how do you smush it all back together? So to do this through a bunch of examples. So say this chunk is completely full. I've used up all of the space in it. And I have a file with inode x in there that I want to grow, make bigger. So what I do is I allocate another inode in another chunk, and I have forward and back pointers. So now if I were to have a problem in this chunk, I could check it, repair it, and then I could follow pointers to say out here and say, oh, this chunk is fine. There's nothing wrong with it. I'll just make sure that this inode exists. Once it's done, I'm going to go back and deal with my own business. So that you can use the same. Sorry. Yes. You can use the same technique for directories, where it's UNIX. A directory is a file. Say I'm trying to create a link to, trying to create a new file. Just in that directory, just create another. An extension of the directory in another chunk, and then allocate the inode there. This is the hardest case. I'm including it. I don't expect you to reason it out or anything, but this was the most difficult case of creating a new hard link to an existing inode inside a full chunk. It still works. This little continuation inode thing is actually pretty useful. So you can definitely get into a state. Oh, I did forget to put those numbers in. You can definitely get into a state where you end up having basically another file system, a normal file system, because there's so many cross-chunk references. Maybe like there's the bouncing free space problem where space frees up in different chunks in different orders, and you end up allocating over and over again from different chunks. And gajillions of continuation inodes, and that's very bad. So you can do this. We know how to do sparse files. We know how to check to see if there's already something allocated in that chunk and use it instead. So yeah?
Are the chunks designed to be laid out in physical block sector groups or
so there's no, you just need to have a simple way to encapsulate operations. So it's very easy to check when I'm working on this chunk. Am I somehow trying to reference outside of it? So I would just do it, and the way I've implemented it is just its length, right? A chunk is these blocks to this block. Yeah?
If you're doing that and it's all in one disk, you've suddenly lost all benefit from being able to get more seeks out of.
Oh, so yeah. So you're saying that if everything's on one disk, you only get so many seeks anyway. Before you had it on multiple disks. Yeah, so if you have multiple disks, you should use them, and there's nothing wrong with Chunkfs. Actually, Chunkfs is very friendly to having multiple disks underneath. So this is trying to improve fault boundaries inside of a disk. So does that make sense? Or okay. Yeah.
Well, what I was concerned about was that if you have, let's say, 3 chunks per disk, or
right.
this would be hundreds of chunks per disk, is that as you have to go back and forth between them, you're having to seek to you're having to introduce more seeks, which will affect this guy.
Right. Yes. So dividing things up into chunks might make your accesses be spread out more over the file system or over the disk, and that would create more seeks, and that would reduce performance. That's what you're saying?
Yes.
Okay. Well, so there's this great thing about the way that file systems are used is that they have locality. And so the problem sort of exists already. It could be worsened by the strict requirements on references inside of a chunk. So what I did is I took an existing file system and tried to simulate, what the behavior would be like if you had to restrict things inside of a chunk. And really, it's not. Things are already fairly localized. When you introduce the chunking, it's only a very small amount of additional work and seeking around. So basically, most of the time when you're doing operations, it's like on a file in a directory, and then your next operation is on another file in the same directory. And you try to keep these all stuck together in the same chunk as much as possible. So all of these locality issues are locality issues you have in normal file systems, and you just use that inside the chunks as well. So I don't know.
The other question I had then was,
sure.
How much of the non-allocation metadata is replicated into the continuation inode?
Non-allocation metadata. As much as you want.
Well, I mean, in your view, things like permissions.
I would go ahead and copy all of the head inode metadata into the following inode metadata as much as possible. So there's also the idea that you might have duplicates inside of the chunk itself, but it's just, you might as well. You've got, otherwise you're just using the permissions to represent no information. So I think you should do more duplication rather than less. Okay. So I wanted to give sort of a visual representation of one of the problems you have to solve with this, which I realized was not in these slides originally. Okay, so say you have this arrangement, you have a continuation inode over here between these two chunks. Say a bad thing happens now. So this gets somehow smashed, which actually I'm going to show you in the demo. So the question is, how do I find this when I correct this inode is going to go away, and then I have this dangling pointer here. So how do I find it? There's actually a really simple solution. It's no big deal. I just have to call it out. So you just have to have a list inside of each chunk of things that are references from another chunk. So I'm in chunk 2, and I have something from chunk 3 reference back and forth. So I just need to have a list of that. And the way I did it is I just created a directory to contain all the references from a particular chunk inside the chunk. So basically, when you have something go wrong over here in this chunk, you check it, you fix it, and then you scan all of the other ones to see that their references into that chunk are still correct. OK, it's fast. Trust me. OK, so I have a demo, which I'm not sure I'm going to keep, or sorry, a prototype, which I'm not sure I'm going to keep working on. It's implemented on top of ext2. ext2 is not a logging file system, and if you shut it down unexpectedly, bad things will happen. But Chunkfs should be able to deal with that, right? So it's kind of putting your money where your mouth is. I have done the file continuation part. I haven't done the directory part. I just wanted to get it working to show people what it's doing. And everything that's not related to mmap works. If you're a file systems developer, you know that mmap is hard. And it's really hard with this structure, because you have a bunch of different file systems all contributing. I'm not sure that that's the right thing to do. OK, so now we're going to do a demo. I know you guys saw me run this earlier, but we're going to run it again. So I'm copying over a disk image that contains an already set up Chunkfs file system. It's got 3 chunks in it. Each of them is an ext2 file system. And they are glued together by this VFS level framework. So there we go. OK, so I set them up. And then this is the command that's stomping on an inode. That's part of a file that crosses chunks. I realized I could actually do this with ATFS debug, but whatever. Anyway, so I have just corrupted my file system. Awesome. now I am going through and checking each of the file systems. Did I do? Yes, I corrupted the first one over here. File system check found that there is an inode. Yes, there's a link to an inode which is not allocated correctly, so which is what I just did to it. Fix, yes. Now this one isn't used anymore. Okay. All right, so that's where we ended when. By the way, I want to point out that my demo worked. Give it up. Yep. Live demos, awesome. But I also managed to do this when I was in Australia too. So, okay, so my little dumb script that does the check notes that chunk was bad because we're going to have to come back later and check everyone else's references to it. But the next thing you do is you check the second chunk, and that is all fine. Nothing wrong with it. Check the third chunk. It is also fine. Great. So now I'm going to mount them and look at the lists of references to other chunks. So this is what I was talking about to get a reference. I'm going to chunk 2 and I'm saying, what are all of your references to chunk 1? Because one of them might be broken now. Look, turns out chunk 1, inode 29. There's a link there. This is a fancy thing to see if that inode is allocated. And it says, no, it's not allocated. So to the Chunkfs file system repair script says, OK, we'll remove that because it's dangling. It's no longer allocated. It's basically an orphan inode. OK, and then we check chunk 3. Chunk 3 has no references from chunk 1. Great, we're done. So that, and then this mounts it to make sure this is all part of my hideous pile of workarounds to make this work. Mounts it to check if it's there. This is a bunch of debug output. Mount big is the file that crossed the boundary that then I destroyed. So we want to make sure that that's gone. That's gone. Then we want to check to see that we found and got rid of this dangling reference from chunk 1, and that is also gone. So that was incremental file system check and repair. It can be done. OK, so some cool stuff about Chunkfs I really like. It's got, it is by design multi-threaded. I mean, what you're doing is you are explicitly calling out the when data operations are dependent on other ones. You can create and delete files all day long in one chunk without having to synchronize with anything going on in any other chunk, because you know that they have nothing to do with each other. They're not sharing any data structures. They're not allocating from the same free space. They're not working on the same directory. So it's really cool. It's really nice when you're trying to do one good thing and you get another really good thing out of it. So always a good sign. Other stuff, so you get the incremental online check and repair, yes. A surprising thing is how useful chunks are for a bunch of file system operations people want to do. Shrink, grow, and defragment. You can, everyone can grow a file system. That's not super hard. Like, oh, change my length. My length is now this. Shrinking is really hard. I think it was like the last thing implemented in ZFS. I'm not actually sure that it is implemented, because last time I asked, they said, we almost have it. It's really hard to have, sorry, not yet? Yeah. It's hard. So basically, you're doing this reverse mapping problem. You have a disk, and you want to remove this part. Well, who's pointing to the blocks in this part? I don't know. I'm going to have to walk from the top of the file system down and find out what points to here, which is slow, painful, but doable, except you have to take the file system offline, because if you're changing things, suddenly you can allocate from there. Or you could fence that off, blah, blah, blah. Anyway, it's hard. With Chunkfs, it's really easy. Who's referencing this set of blocks? Well, only references inside of this set of blocks. Okay, so fence it off, stop allocating from it, move things. You don't have to walk all the way down from the top of the tree. You just have to walk from the top of that little chunk and move all of that stuff. You can also do all these kind of cool things that people keep coming to me with new ideas for how to use this, where you can defragment your system by shrinking it and then growing it again. Or even cooler, you can have a different file system layout for each chunk. And if you decide that you want to change what those layouts are, you can shrink it, take away those chunks, and then put them back in a different format and reuse them. So if your file system is changing use cases from a lot of small files to a lot of big files, you can reformat that way. I have this idea of the one big file system, where it has one inode and the rest of it is just the file data. You could do that for individual chunks if it worked out pretty well. Crash-only software is this pretty cool idea, which is somewhat misunderstood, which I thought was pretty awesome initially, but I had no idea I was building something that was crash-only. Crash-only software is this idea of your system has to deal with crashes happening. It has to behave correctly, and it has to recover quickly. So as long as you already have these requirements, you might as well say that you're going to take advantage of that and shut down the system by crashing it and recovering it. So one, this is going to be fast because it has to be fast. And two, you're going to be testing the code for crash and recovery all the time. Or you could just be like OpenOffice and unnecessarily recover frequently. But crash-only software does not mean that you don't make an effort to save data, get it written out to disk or anything like that. But yeah?
So based on your description, it looks like this file system is not at all concerned with data recovery.
No, it is about data recovery. It's just acknowledging the fact that data loss occurs and dealing with it quickly. So crash-only software I'm describing, I was just about to say that that's the misunderstanding about crash-only software that people need to understand. Crash-only software is not about, oh, oops, I tried, I'm just going to crash now. Crash-only software is saying, I am going to be aware of the fact that I'm going to crash and try to get things to operate in such a manner that if I do crash, the badness that happens is minimal. So in non-crash-only software, you're going to save up a bunch of changes and then not actually write them to disk. In crash-only software, you're going to write them to disk frequently, instead of waiting until the end when you close the program. I'm sure Firefox used to do this. You change your preferences, and if it crashed before you actually quit officially, it would not save the freaking preferences, right? That was incredibly annoying. To make it crash-only, you save it right then, not waiting until this. One of my friends put it this way. All of the code that happens in your close function, the explicit shutdown function, it should be, there should be a comment at the top that says wishful thinking. It's like, sure, you get to run that if the stars align, if I didn't just Control-C that program, that kind of thing. So another aspect of crash-only software is that it says to build things in small rebootable pieces so that you can have a bug or an error or a data problem in one small piece, and then you can restart that piece by itself. Everything else keeps running along, and then that part starts operating again. So that's what the chunks are. You can cut them off, fix them, unmount them, remount them. Everything else just keeps going. OK, I think. OK, this is where I admit why this will never work. And I'm not the only person who thought, oh, hey, I'll just take a bunch of little file systems and, in reality, in implementing it and glue them together. In the end, I don't think it's a good way to go long term. There's all these annoying issues, so the logs are a good one. I'm using ext2. I like ext2. ext2 pretty much works, but in reality, you should probably have a logging file system inside of each chunk. And then you have a bunch of logs, one per chunk, and logs have to have memory pinned for them, and then you have to write out to them, and then you need a log across all of the chunks, and this ends up looking very bad and not like something you actually want to do. So I just kind of punted on that issue. And then the next thing I realized, and this has applications for all kinds of other things that people are trying to do. So the way that you do a lot of people are trying to do this kind of thing on Linux, where each file system exports a set of VFS operations, like allocating inodes and creating directory entries and things like that. And then the VFS sits on top and does all the permission checks and things like that. Well, a bunch of people are trying to get in between the VFS and those file system operations. They're calling this stacking file systems or layered file systems. Chunkfs is only one of a long line of file systems trying to do this. I finally concluded that we're doing the wrong thing. There's these great little interface, little functions sticking out of the file systems that are intended for use by the VFS. We shouldn't be using those. They're just not the right operations. We end up having to fake up a bunch of stuff and pretend that we have weird structures that we don't actually need and we don't care about when we're doing layering file systems. So I actually think that there should be an interface inside of the Linux file system stack that says, and this is for stacking file systems, because this is what stacking file systems really want. They really want to just allocate this inode. They don't want to create a D entry for this, that kind of thing. I would love to get somebody to agree with that and start working on it. So that's what the lower level ops is about. OK, questions on my super fast Chunkfs presentation?
So sorry, I kind of asked that out of order. I agree about designing with crashes in mind. So while admitting that, when I asked about, do you replicate all the data to the continuation inodes, the possibility being that you can use them to recover the corrupt.
Exactly.
Right. But the downside being that now every time I do a chmod, it's got to write to every chunk that contains any of the data for this file.
True.
Right. Which for a lot of files is going to be spread across a lot of chunks.
Yep.
So now I've got a synchronous operation across 6 chunks, which could be on the same disk or on separate disks.
It doesn't have to be synchronous. Logging still works. So you can write a log entry that says change this and then do it in a lazy manner. So, because the thing about a lot of this stuff is that when you're writing redundant data, you don't have to do it right away. It's not an issue of correctness. It's an issue of how big the window is during which, if you lose this data, you also you lose it overall. So. I mean, there's a bunch of, there is cost. I've done some mathematics on the cost. It doesn't look like it's a big deal, given most reasonable file systems. So most files are, in most cases, 50% of your files are under 4K. They're not even going to be in more than one block, much less more than one chunk. So.
Given those calculations, what kind of chunk size are you imagining? It's like 100 gigs, 10 gigs?
I did some math and showed that I think it was a gigabyte was fine, right? And that's so tiny. I mean, how long does it take to check a gigabyte? A second, 2 seconds? And I did some math on, and then include checking all of the references in all of the other chunks, and then assume that it takes a worst case seek every single time to get one of those references and deal with it. And it was like, then you added 2.5 seconds to the 1 second check time. So, it really has, chunk size is really dependent on how localized references are inside of the file system. And references are pretty localized. There's very few hard links. Most files are small. Most files are located near the directory that they're referenced from. So. I was really pleased with that result. Like, wow, a gigabyte, cool. I mean, what can you do with a gigabyte?
Well, it seems like then you'd have, if you have your chunk size of a gigabyte, a lot of the files you'd be interested in will probably fit within there, but some of them will span many, many chunks.
Maybe, yeah.
Most notably things like database files,
right?
Data files, those are the ones where you care about performance usually. Playing tricks, trying to guarantee some sort of contiguous allocation. To what degree will this?
So, I mean, it is effective. It can be effectively contiguous. I mean, you lose most of the benefit from contiguous allocation at contiguous allocations of above, 256K. So at that point, it kind of doesn't matter as long as they're fairly close. Yeah.
You could have different chunk sizes too, right?
Yes, you can have different chunk sizes as well. So.
Is there some mechanism to get the big files in the big chunks and all that?
Well, so one of the nice things is that all of the algorithms that you want to use to defragment things and keep things local and try to allocate them sequentially in chunks are exactly the same algorithms that we already had to develop and use in modern day file systems. So you're just adding a little layer of indirection between things. In existing file systems, you want to lay them all out sequentially. In Chunkfs, you'll want to lay them out sequentially inside of a chunk. If you can, it'd be nice to get it sequential across chunks, but it's not a big deal. So, yeah?
Do you intend to need a host file system, or would you just allocate some LVM extents to it?
Do you need a host file system to back the chunks, or?
Yeah.
Well, the thing is that once you have a file system inside each chunk, they don't have to be contiguous. They can all be located on different devices. Personally, I'm an advocate for folding the the volume management layer into the file system layer. I think that taking a disk interface and exporting another disk interface above it is very bad. You lose a lot of information. You introduce another layer of indirection for not a whole lot of purpose. So. I have failed to mention that ButterFS, BTRFS, is a new Linux file system, copy on write, checksum, storage pools, all that kind of stuff. The author, Chris Mason, is at least taking very seriously these concepts and trying to build them into ButterFS, so trying to compartmentalize metadata in such a way that if something goes wrong here, you can repair it without looking at things outside of it. So like splitting up the free space map is one of the major things. So that may be the future of these ideas, is actually being inside as part of a file system, being designed in from the beginning, like I would like to see. So. OK, I think, oh, wait, sure.
Do you put any thought in any sort of generational thing, kind of like a generational garbage collector to keep some chunks is not changing? Because it seems like the time to recover is proportional number of chunks that change.
Yeah, well, so I actually did some measurements on that, and most, sort of simulating again, this is a chunk. Most parts of the file system are idle most of the time, like 98%, 98% of the time, that sort of thing. Generally speaking, not a lot of stuff is undergoing any sort of change. But just because it's actually active and changing doesn't mean that you have to check it. In this particular implementation with UXT2, yes, you do. But in a smart way of doing it, you would only check things that had a problem with them or were related to something that had a problem. So does that make sense?
Yeah.
OK. All right, OK. I think we're done. Questions? Appreciate you guys coming.